Hello, my children of the internet. Welcome to whatever the fuck this is. This is the Introduction to Coding Lesson 4, take 2. So this is going to be on some fun stuff. There won't be too much coding, but there's hopefully going to be a lot of knowledge that I get to impart on you as part of this. This is going to be on data types and variables. And it is one of the more important things in coding to understand. But it's a very broad topic, and I'm just going to be teaching you the basics of how data works in a computer program and how the computer stores it. And also I'm going to go a little bit into numbering systems. I'm not going to do too much about numbering systems. If you don't know the difference between something like binary, decimal, hexadecimal, that kind of thing, I'll go into it just a little bit, but I would highly recommend you look into it a bit further if you don't completely understand it, because this is not for that, but it will help a little bit of the representation of certain things. Which reminds me, I have to actually open... Oh, I've lost my mouse. There it is. Okay, I have to open something over here and get ready for you. So, first things first, what is a variable? Now, in terms of... well, in life, something that's variable is something that changes. And that's pretty much what it is in computer programming as well. So to sort of demonstrate that, this is our program from last week. Now we're gonna not do that, or from last lesson, I'm not gonna say last week, so it wasn't last week. So if you, I can't remember if I described how you create a new project in this, but we're gonna go right click our solution, go add new project, and we're gonna create an empty project called lesson 4. It's going to lag out for a little bit, and then we're going to add our file called main. And we are literally just going to copy and paste this code over. Now, if you hit run now, it's actually going to run lesson 3. You see it bolded here. So we're going to right click lesson 4 and go set as startup project. I don't think I need to explain what that's actually doing, but in case I do, that's the default target for when you hit the start button up here, or you press F5. So what are data types, what are variables in computers? So a variable is a combination of a few different things. It is a data type, it is a location in memory, and it is an actual piece of data, all at once. So let's look at something that we actually did in terms of last week. We have the number 0 here, and we talked a little bit about the int. So if you don't remember, an integer or an int is just a number that doesn't have a decimal point, sorry. So it's a whole number, so 0, 10, 500, a billion, whatever, whole number. And when you want to create a piece of data that is an integer, the computer needs to know what kind of data type it is. And an integer is a data type, representing just a number. There are many other data types which we will be going into in a little bit, but let's concentrate on int because it's very, very basic. It is probably the second most basic piece of data we got. And the other one is a little bit too basic, and this is also a good example. So let's leave our code there and let's talk about integers. So, or more specifically, how we create one. A variable in a computer program is made up of 3 things. At least to the user. It is a data type, and sorry, I'm going to preface it again by saying at least in this language, and in some other languages you can do some funky things, but in this language it's what's called as strongly typed, which means you have to give it a data type. It has to be a concrete type that it knows of to create a piece of data for. So the 3 things you need are a data type, an alias or a name, and a piece of data. That third one is semi-optional sometimes, but we'll go into that for a little bit. So let's create ourselves an integer or any data type. Now in C++, the syntax or the way you do it is exactly this. You go data type, so data type, then name, and then if you want to assign something to it or create the piece of data for it, you know what, let's just keep it simple. And something I didn't explain in the last lesson too was comments. I know I'm sort of jumping a bit all over the place here, but it's sort of all going at once. A comment, if you put these 2 forward slashes in, the text goes green and the program ignores that piece of text for the rest of the line. So commenting, it allows you to put text that doesn't affect the program. Stuff like, this is how the program works, or this is what I've done this for, or please the next person who does this clean up after me, because that's something I might have done a couple of times before. Anyway, so let's create a piece of data. Let's create ourselves a data type int. Pretty simple. Let's call it test, because test is pretty simple. And then like our piece of code down here and our piece of code down here, let's end it with a semicolon. We have just created a piece of data. Well, at least a placeholder for one. It is an integer and it is called test. This is me, the equivalent of me telling you, hey, I'm going to give you a number that's going to be for test. Or it's going to be my home address number, or my phone number. Now, you wouldn't really store a phone number at an integer, doesn't make much sense, but let's roll with it. Let's say we're the police and our phone number is 3 numbers, and that will work. Or we live back in like the 1920s, whenever the phone was invented, and we have very, very small phone numbers. So cool. Well, I've told you that I need you to store my phone number, and it's going to be a number, an integer. What is it? How do we give it value? Well, we can do it in 2 different ways. You can do it like I'm doing now, which is I'm going to tell you you're going to be storing something and tell you what it's called and what it is. And then I'm going to go and tell you what the data is, a bit later. This is a fairly common practice for certain types of functions, depending on what you're doing. So I'm going to show you both ways. So to assign some value to a piece of data, we're going to go the name of the piece of data, which is my phone number, equals 000. Well, let's do a number we can actually see, because 000 is just 0. It's good 911. Let's pretend we're American. Then end it with a semicolon. So once again, this is the real world equivalent of me saying, hey, I need you to hold a number for me. It's called my phone number. And you're going, sweet. And then I go up to you a little bit later and say, my phone number is 911. And you go, sweet, it's in my brain. We're good to go. Pretty easy. But that seems like, at least on surface, a little bit inefficient, right? You're doing it in 2 steps. Why are we doing it in 2 steps? Now, as I said, there are reasons you will need to do it in 2 steps. But in this case, we don't really need to. So how do we get around this? Much the same way. So to create the piece of data, the variable, and assign to it in the same line, we can do something like this. It's data type, name, equals value, and a semicolon. So I want you just to pause the video for a second and tell me what I'm going to type here. Okay? You got it? It is this, int my phone number 2, because everything needs to be uniquely named, because how will it know if I tell you, hey, I need you to store my phone number, it's 911, and they go, hey, I need you to store my phone number, it's 222, you're going to be like, I'm confused. I'm going to say 222. Just like that. And that is the 2 different ways, 2 of the very different ways you can create a piece of data. Now, on the surface, this is pretty simple. You're giving it something to store, you're giving it a name, and you're giving it the value that it needs to store. So once again, the real world example of this saying, hey, I need you to store a number, it's called my phone number 2, and it's 222. All in one big sentence. Easy. But what are we actually doing here? What does this do? Well, I have my handy dandy Excel here to help you. We just adjust this column. Oh, I made it too big. All right, cool. So what I've got here is an extremely basic representation of what memory looks like. Oh, this is not hexadecimal. I can't remember if you can actually do that. can. Des to hex. Ah. Wow, I broke that something fierce. Okay. I will just type it in. 1018. No, I've forgotten how to be a programmer. Hang on. Okay, apologies for my sort of half meltdown. I forgot how to count in hexadecimal, which is not something you do very often, funny enough. And okay, that's why that's there. Cool. So what we have here is an extremely basic representation of computer memory. Okay? And this is an old school integer where it used to be much, much smaller. Now we have much more RAM, we have much bigger processing power. Our numbers, they're pretty big. You used to be able to hold between 0 and 255 in an integer, and now it's between 0 and 2.178 billion. Some large number. The number itself is somewhat irrelevant to what you're doing, unless you're trying to store numbers more than 2 billion, then it will become more relevant. But let's talk about binary. Now, binary and decimal and hexadecimal, they're all pretty simple numbering systems once you figure out exactly what the formula is. And let's just quickly go over it. And once again, I said this at the start. If you don't quite understand binary, this is a very, very quick run through. But if you don't at least grasp the concept, I highly recommend you go watch some videos, read a book, something. Because as much as it isn't completely relevant to what we're doing, it is something you really should know. Okay, so let's talk about decimal numbers. Let's talk about the number 935. Let's make this font a little bit bigger. Now, how do we know this is the number 935 in a decimal system, which is what we use? We have decimal, deci, which is 10, or dec, sorry. We have 10 digits we can represent our numbers with, 0 through to 9. 0 being the smallest, 9 being the biggest. And we know that once you get to 9, you start again. It goes back down to 0 and you carry one over. You have 10. Much like decimal, binary does pretty much the same thing. And so does hexadecimal. So does basically every numbering system you can think of. They're all exactly the same. So let's show you the decimal representation of 935 and how we break it down. So 935 is 900 plus 30 plus 5. Because those are the 3 digits we have. We know that. How do we get to this? Okay. So let's go from the 5. 5 is equal to 10 to the power of 0 times 5. So this is the formula for working out what... My brain stopped working again. What number value each one of these digits actually is. It is the numbering base, which is 10. We have a base 10 system. We have 10 digits. To the power of the position. In this case, we're going right to left because that's how we read numbers. Times the value of the digit. So we have a 10 base. We're in position 0. And we're timesing it by 5, which is the number there. Anything to the power of 0 is 1. Anything to the power of 1 is itself, etc., etc., etc. So this is equal to 5. And then let's go to 3. I don't know why I did like that. Okay, let's go to the second digit. So the second digit is 10 to the power of 1 times 3, which equals 30. Because it's 10 times 3. And then we have 10 to the power of 2 times 9, which is 900. Because 10 to the power of 2 is 10 times 10, which is 100. Now, if we were to add 156 on the front here, we can just keep going up. 10 to the power of 3 times 6, which equals to 6,000. 10 to the power of 4 times 5, which equals to 50,000. And 10 to the power of 5 times 1, which is equal to 100,000. Now, if we line all these guys up, I don't know why I did that so stupidly. we get, oops, 1, 5, 6, 9, 3, 5. If we add them all up. That's it. That's how you, and you know how to do this. In your head, you already know this. It's just seeing it as this formula, you kind of, I did it to me, it sort of sent me through a bit of a loop. Well, okay, we have this, so how does this relate to computing in binary? Well, let's say we have a binary number. Now, a binary number, bi is 2. We have 2 digits to represent our numbers, 0 and 1. That's all we have. So we can make up numbers with anything from 0 and 1. So let's give a good one. That is something that I actually remember the number of, 1111, 1111. I can tell you right now, this is 255 in decimal. This right here, in binary, so it's in base 2, is the same as 255 in base 10. Base, once again, is the amount of numbers or digits you have to represent your numbers. We live in a binary society, in a digital decimal society. Everything is in base 10. Your money, your measurements, all that kind of stuff, all the numbers are base 10. So how do we work this out? Let's go back to the formula. Base times position, base to the power of position times value of digit. So the first one is easy, 2 to the power of 0 times 1, which is equal to 1. Because anything to the power of 0 is 1. Then the next one, 2 to the power of 1 times 1 is equal to 2, because anything to the power of 1 is itself. I said 2. Don't ever do that to me again, Notepad++. And then we're going to keep going up, and it's going to keep going up, because 2 to the power of 2 is 4 times 1. And let's just 3, 4, 5, 6, 7, which then is 8, 16, 32, 64, 128. Now you can see a clear pattern here, it's doubling. Because it's in base 10, base 2, we're going up by the base each time, times itself. Look back over here. 10 to the power of 0 is 1. 1. 10 to the power of 1 is 10. Then times by 10 is 100. Times by 10 is 1,000, etc., etc., etc. Yes, sorry about that. So that is how a basic numbering system works. Now hexadecimal is 16, works much the same. You have 0 through 9 and then A through F. And you do use hexadecimal a little bit, kind of, but it's not as prevalent. So we're going to skip over that, but it's the same kind of formula. So yes, much like you could put a 0 in here, 150935, and then this one would be 0, and that'd be 0, and etc. You could do the same thing here. Cancel that one out, cancel that one out, cancel that one out, and that becomes 249. Cool. We know how binary works. So let's go to this cool Excel spreadsheet I've made. How does a computer work? Well, when you go, hey, I need to create a data type, the program goes, all right, let's go find some free memory somewhere. Doesn't really matter where. Cool. Here you go. It's that memory address O times something in hexadecimal that I said we don't really use too much. Cool. So it starts at O by however many bits you have on your CPU. And it goes all the way to O times F, however many bits you have on your CPU. We're just going to pretend we're going to start at the very top of memory, the very first bit in memory. What's that word, bit? What is a bit? Well, I'm so glad I asked myself. A bit is the most basic kind of data in a piece of in a computer. It is either 0 or 1. Why 0 or 1? Think about a light switch. How do you get something else besides on or off? And when it's not on or off, you have like a dimmer switch. How do you tell the difference between 49% brightness and 50% brightness? It's pretty difficult. So computers just store stuff in an on or off state. Now that is an extremely, extremely simple version. but it works. That's pretty much how it does it. And then, okay, so you may have heard byte, kilobyte, megabyte, etc. A byte is 8 bits. Why 8? I honestly can't remember, but it was some stupid thing about the way characters are stored and stuff. It honestly doesn't matter. It just is what it is. A kilobyte is 1,024 bytes as opposed to like a kilometer, which is 1,000 meters, because 1,024 is the nearest power of 2 to the power of a number I cannot remember for the life of me. It'd be like 10, 12, 16, I don't know. Doesn't matter. It'd be 10, I think. Okay, I gotta find out now. So that's 2 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 2 to the power of 10. Cool. And then at megabyte, it's 1,024 kilobytes. But depending on what you're buying, you'll get 1,000,000 bytes in a megabyte. Or if you're buying a hard drive, if you're getting internet, you'll get that much. 1,024 times 1,024, whatever. So it is a little bit dependent, but in the case of memory, we're talking about 1,024 blocks, not 1,000. And here we've got a nice formula on how to actually work out how much this binary value is. If I type in a 1, or if I give you the example of this one, which we did before, just 255. But let's just erase it for now. So it goes, okay, here's a block of memory you can have. You've asked for 1 byte, 4 bytes, 100 bytes, whatever you've asked for. Here is where it starts. So in this case, we have asked for my phone number. And now 911 isn't actually going to fit in our memory. So I'm just going to change it to 111. Now 111 is that. So now we have a representation of how our computer is actually set out, how our memory is actually set out. At memory address 0, we have my phone number thing is stored there, and it's stored as 01101111. That is a 111 in binary. And then we have, sorry, I keep clicking the wrong thing. Let's get rid of this, rid of there. My phone number 2, let's say it gets stored at memory address 20. It is also an integer, but it's 222, which is there. 1101110. There's a bit of space in between. I mean, it's inefficient, but it doesn't really matter. I don't think it generally lays it out like this, but it depends on what your program's actually doing. But there, we've just created 2 bits of data on the computer and given it values. And this is a fairly accurate representation of how a computer actually interprets your data and stores your data. So then, this alias here, my phone number 2, it doesn't directly store your value. What it stores is the start of the memory address. So this one here is actually equal to this, 0020. Now this is extremely low level. You don't need to know this, but it's good to sort of have a little bit of a handle on how memory works. So when you try to pull this data out, what it goes is, okay, this is an integer, I need a byte. In this case, in actual programming, it's actually 4 bytes, but I'm too lazy to make this 4 times longer. So it's 4 bytes, so it's 1 byte in this case. So I pull 1 byte out, which is all this, and then the computer knows how to interpret, or the program knows how to interpret that as an integer, which will be the number 222. Now, we can actually show this at work. In the next part of how you actually use data is, how do I get it back? So I've just told you to store my phone number is 111. And then I go off to my day and I come back at the end of the day, hey, I forgot my phone number, what is it? Oh, it's 111. What's my phone number 2? It is 222. It's exactly how you get data out of the computer as well. You refer to it by name. So this here is a special case hello world. We will go into that. But let's say now we want to print out my phone number to the screen. We just go like that. Instead of the string of text hello world, we're now saying, hey, please print out my phone number to the screen. Now I'm just going to very quickly add something. All right, apologies, my brain stopped working for a second there. Just ignore the 4 extra lines or the 3 extra lines of code I've added. They are just to stop the screen from immediately disappearing, us having to go to the command line and doing all that bullshit because I'm too lazy to do it. So let's build, and let's show my phone number on screen. What is going to show up? Ooh, I wonder. It's going to be exactly what you think it is. 111. Cool. We have now successfully created a piece of data, assigned a value to it, and then retrieved the value. What else can we do? Oh, I'm so glad you asked, Mr. Imaginary Person that is actually me. Well, we can create different pieces of data. We can create more data. We can manipulate data. We can do all these kinds of fun things. So let's do one fun thing. Okay. Let's change the value of my phone number. How do you think we're going to do that? Dun, 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 dun. Time's up. You can pause it. To change the value of a piece of data is exactly the same as assigning value to a data, because that's all you're doing. You're just assigning data to the value to the data. So in the case of my phone number, if I want to change my phone number, if I want to go to you and say, hey, my phone number is now 112, that's all you have to do is go, hey, my phone number is actually 112. Cool, I've stored it. So let's start the program again. You'll see it's changed. It's as simple as that. Assigning and reassigning is the same thing. Even if you create data this way, which is the one-line way, you can still reassign data the exact same way. It's the same syntax, it does the same thing. Just like this 2-line piece of code here and this 1-line piece of code are literally the same thing. This just looks a bit neater. And sometimes you want that. A lot of times you want that. You always want it to look as neat as possible. Let's just say that. You don't want your code to look shit, because then it's hard to read. And the easier it is to read, the quicker you can interpret what's happening and look through it and then sort of figure out what's going on. Cool. So we have integers. What else do we have? Well, let's go back to our hello world example for a second. We have this piece of hello world. We all know what this is. This is a piece of text. So what is a piece of text? Well, a piece of text is made up of 2 things. Well, one thing, really. It's made up of characters. It's things like the letter A, or the number 1, or the @ symbol, or the when you press the enter key and it goes down on the next line. That's a character. You don't see it, but in your text file, you go to Word and you hit enter and you save it. It needs to have some representation of that new line. There's blank space to you, but the computer needs to know how to recreate that blank space. So that's called an n-line character. You can probably figure out why. So this is what I brought up before. This is what's known as the Ascii table. Now, Ascii was like an organization that came up with the standard representation of how characters are stored in memory. So you have your decimal representation, which we just spoke about. You have your, I've forgotten, the hexadecimal representation, which is your 16-character representation, and your octal, which is your 8-character representation. And then you have the actual character itself. So if we look at, say, capital A, you'll see that is represented by the number 65. Now, let's create a piece of data and then see how it looks in memory as well. So a character, much like how an integer is an int, a character is called a char. Char. So you should know what we're doing from here. How do we create a character named test character? Exactly right. Now let's modify this to do the single line assignment thing, just like this guy here. I'm just going to zoom in a little bit so it's a bit easier for you guys to see. How do we do it? I bet you're going to think this. And unfortunately, you'd be wrong. If we were to try to compile this, and you'll see the red squiggly line on the screen, it's giving us an error. Can you please show me the errors? Error list. Identifier A is undefined. Well, what does that mean? You can hover over it and also say the same thing. One of the basic things about Visual Studio is if you see a squiggly line, something's gone wrong. A green one means it's a warning, and a red one means you fucked up and the program's not going to run. At least most of the time. Sometimes it gives you false warnings, but then they work and then they go away after that. Anyway, the reason numbers work is because C++, and I think most coding languages in general, when it sees a number at the start of a piece of code, it goes, this is a number. Perfect. You don't have to tell me anything else. The rest of this is a number. That's why if I go 222A, it's going to correct the shits. Use it to find literal operator not found. Because it doesn't know what an A is in terms of a number. But a character, this A could be a piece of data, it could be a function, it could be another program, it could be anything, because it starts with a letter. So how do we tell the computer that this is actually just a character? Or much like when you quote someone, you put these single quotation marks around it. And now it goes away and says, cool, I know exactly what this is a character A. So let's print this out to the screen. Let's print out test character to the screen. Now, if you don't remember what cout and endline and all this kind of stuff does, go back to the last lesson. But just a quick refresher, this is basically saying this is a representation of the screen. This is some data we want to put on the screen and some more data we want to put on the screen, shove it all on the screen. It's a little bit more complicated than that, and we will go over that in the next lesson, but for this lesson, I think that's good enough. Now you'll see here it still says there's an error, but once we run it again, the error will go away. And you'll see we have the two previous numbers, 111, 112, and then our new letter A. Well, cool. Okay, so how does that represent it in memory? So what do we call this character? We called it test character. So let's put it in position 10. So what does it look like? Well, we know what the decimal representation of it is. It's 65. So much like if it was just the number 65, it's actually just represented like this. And you can see that's just the number 65. If you do the binary math, it's just the number 65. But because we've told it that the data type is a character, it's going to go, okay, this is how I represent it. It's not a number, it is not the number 65, it is the character at position 65 on the Ascii table. It's a little bit more complicated than just an integer or a number, but not too much. And the wonderful thing is an integer and a char can actually be interchangeable. If I want to say, to print out the number represented by this character, you can actually do that. And if you want to print out the character represented by a number, you can also do that. We're not going to do it here because it's a little bit more advanced, but you can. They are somewhat interchangeable. Okay, cool. You told me how to store a single character, but when you write something, you generally write more than a single letter, and you don't have to make test character A, B, C, D, and then sort of mash them all together. If I want to type in my name, I don't want to have 5 different pieces of data. It's one thing, it's my name. And you're absolutely right. And I'm just going to go back over here while I highlight this line. And I want you to just look and see the difference between me saying A as our test character and hello world as our piece of data here. Now, if you want to do a sentence, so more than a single character, you need what's called a string. It is a string of characters. It might be a term you are familiar with, having a string of things. If not, just basically think like a big bunch of characters on top of a string, all joined together. I want you to remember what I had highlighted. So now strings are a funny thing. And I'm not going to explain it. But I am going to write it down because I don't think I have it. That's part of what I need to explain in these lessons. Now, much like you see here, this SED : I think we spoke a little bit about that. It's a namespace. We're not going to go into it yet, but the string It isn't something that the actual programming language understands. Unlike an int, it knows what an int is. C++ knows what an int is. C++ knows what a character is. C++ knows what return is. C++ does not know what a string is. And there's a reason for that, but it doesn't matter. It comes with a string, but the actual language itself doesn't understand it. So what we need to do is we need to go grab someone else's representation of a string. And thankfully, if you remember the include thing, you can actually include a representation for a string. And it's in the std namespace again. So we're just going to create our data type of std string. It's no different to using a character or an int. It's just a different name. It's got a couple of colons in it. It's got an std. It doesn't matter. It's all the exact same thing. And we're going to call it test string. And we want to give it a piece of data. Let's give it, wait, I got my left and right mixed up. This thing here, Megadeth, because it's on my jumper and I like it. How, and I want you to think back to what we just saw on the screen. How do we represent that? Because remember what I told here, this is a single character. When you use a single quotation mark, you can only hold a single character. So how do we represent more than one character? How do we represent a string? Well, we do double quotation marks. Much like our hello world example here, we had the double quotation marks because hello world is more than one character. We use double quotation marks. Now, you'll notice that there's no red squiggly lines, and if I was to go and compile this, you'll see it's actually successful. But I thought you said more than one character. Yes. But you can also have less than one, or one exactly. There are specific cases when you want to use a character, like this, but for the most part, you're going to be using strings. A single letter is a string. No letters is a string. No space is a string. The enter character is a string. They're all strings. It's all fine. One character is also a string. But in this case, our string is something called Megadeth. Or like the logo, I guess, with a capital H at the end. And then of course, because we're testing it, let's also print it out to the screen. You'll see it's the exact same code, just with the name changed out. It's all the same. All the syntax, all the way you do it is exactly the same. And there it is on screen, Megadeth. Okay, cool. So how is this represented in memory? That one, you have to wait a few lessons for. But I want you to see if you can sort of, bounce it around in your head. How do you think that's going to be represented in memory? And if you've watched to episode or lesson 1, 2, 3, 4 from now, it's like 7, I might mix it up. We'll see if you're right. Okay, cool. So we've given you 3 data types, int, character, and string. What if we're doing financial calculations? What if we're doing trigonometry? How do we represent those kinds of numbers? Things like pi, which is got a decimal place, it's 3.14159. What if we're doing money? I got $8.10 in my bank account. How do I represent that? We use a couple more data types. There are 2 more data types, and there's also, I think, a few more as well, but they aren't as relevant. So we'll just go into these basic ones, and then as the other ones pop up, which they might actually not because they don't get used a whole lot, at least in my line of work, we'll sort of dig into them a little bit more. So the first number we want to do is we're going to do pi, okay? So pi is 3.14159 billion other digits afterwards, okay? How do we represent a number with a decimal place on a computer? The underlying math and memory management to this is extremely complicated, and I only very, very barely understand it. I will fully admit that. It is so confusing. And it is very hard to explain. But it has what's called a floating point. And this is something you might have heard before if you look up like graphics card calculation, graphics card power. You have this thing called flops, which is floating point operations per second. So a floating point number is where the decimal place is not fixed. It can actually go left and right in memory. The amount of data it's stored is still the same width. You still have 32 bits or 4 bytes or whatever it is on modern PCs, I actually forget. But the decimal place is not fixed in the middle, because if you want to have like 1,000,000.1 or you want to have 1.357836531, you don't want to have to sort of guess where that decimal point needs to be, because then you have all this wasted space. So you have a floating point that can go left and right depending on how big each of the numbers are. But this comes with a catch. Floating point numbers are extremely, very rarely exactly what you type in. And pi is actually a good example that I found out when I recorded the first take of this. So much like character and integer, a floating point number is represented by a smaller word, float. So once again, I'll pause the video, or I won't pause the video, you should pause the video. If I want to create a float called pi and assign it 3.14159, what do I have to type in? You got it? Cool. So what's this? I need the 2 on the end. I'm pretty sure it's a 2. Excuse me. So let's also shove this out on the screen. Now, what would you expect to come out on the screen? You expect 3.141592. And unfortunately, you don't get that. Which I think I actually just saw why. Yeah. Let me just try one more thing, and I'll explain it in a second. That's fine, okay. So you might not have seen that, but I'll make it happen again. So down here in this little thing here, you'll see truncation from double to float. It's cheating me, not being able to explain to you what a double is. But when you represent actually gives you a nice representation of what the float actually looks like in memory. But when you want to say it's a floating point number, you have to actually postfix it with an F. This number. This is a floating point number because you can do a different kind of number with a decimal place, which we'll go into, and if you're half clever, you better figure out what it is. But it's not an accurate representation of the number. If you have a look there, it's actually 3.1592026. Where did those extra numbers come from, and why doesn't it display properly on screen? This is the inherent flaw in floating point numbers. You don't have very many digits of precision, and the amount of digits you have is never guaranteed. Never. When the number's small, you have a certain amount of numbers that you're likely to have. When the number is small, you're going to have more precision. But as the numbers get bigger and bigger, you have less and less precision on the decimal places. Now, this all sounds very, very confusing, and you might not actually run into anything like this. But if you're starting to do calculations using something like pi, or like something with 1 billion decimal places, and it's like, oh, why is my math off? The computer says it's wrong. Just double check it, because it might not actually be correct. On the computer side, that is. Computers are not flawless because computers are made by humans. Just remember that. Well, okay then. So what happens if I am doing something important that needs precision, like money? You don't want to fuck with people's money. Well, there's another data type, which we spoke about, which you might have already guessed what it is. It's called a double. Now, once again, I just want you to imagine, you don't have to pause it. I think by this point you probably get how to do it. I want you to create a double called my bank balance and assign $8.10 to it, or $8.10. Okay, so double my bank balance equals $8.10, or even 8.1, of course, because that's the way decimal places work. So let's say 8.15 then. Now you'll see on the screen here is actually represented by 8.15, what is that, 0.000000000000000000355. So you actually have a little bit of inaccuracy, but those first 2 decimal places are guaranteed to be correct. That is why it's called a double. You have 2 points of precision. And to be honest, that's generally enough. And there it is, 8.15. The rest are kind of best guesses on what it needs to remove, but it's once again, it's not exact. A double, you can always trust that the first 2 decimal places are correct. The rest, you cannot. If you need something more precise than a double, you have to go write it yourself or download someone else's library. If you need something more accurate than just whatever it wants to give you with the decimal place, you can't use float. It's as simple as that. Float is good for a lot of things, but not for everything. I've had issues in my game engine where it's been out by, a fraction, and it's thrown out all my calculations in graphics rendering. I'm losing my mind. It's like, it's right, the math is correct, why it's not working. And then I correct for the floating point error, and it starts working. I'm like, you fucking arsehole, and I throw something at the screen, and this totally didn't happen. Yeah, sure. So cool. We have learned a bunch of data types. This is actually enough to make a very basic program. What can we do with this? As I said, very basic. We can print stuff to the screen. We can assign data and store it and retrieve it. It's not a whole lot. But let's talk about something else. Let's talk about best practices and conventions, and then let's talk about something called a constant as opposed to a variable. I want you to try to guess while I talk about best practices what a constant is. I'm sure you can understand it. So you'll notice some of my naming schemes here. So say my phone number. We have a little m, little y, capital P, and the rest of phone, capital N, and the rest of number. This is called lower camel case. Everyone I've ever worked with has used lower camel case as standard for variable naming because it is extremely easy to parse in your head once you get used to the thing. Like you sort of go, oh, okay, so every capital letter is a new word, so that's just my phone number. It's not my phone number. What the fuck's that? Like if that was all lowercase or even all uppercase, it's a lot harder to read. Ignore the squiggly line, it's because things. So that is one of the best practices I can really give you. On top of that, actually naming the variable something that's meaningful to the piece of data it holds is invaluable. Do not get in the habit of calling things A or test like I've done here. I could call this thing here pi, I could call it test, I can call it circle namey thingy. That makes no sense. You call it pi though, and you go pi, I know what pi is. Pi is the squiggly. Cool. I have my bank balance. I could easily call this but that makes no sense. And once you're reading through, a few 100,000 lines of code a day or whatever it might be, you want everything to make sense instantly. And if you don't, the people you work with definitely do. So use proper names, and if you're not going to use lower camel case, use underscores to represent spaces or something like that. There's also upper camel case, which is the first letters are capital. Once again, generally everyone I've worked with has used upper camel case for function names. Now we haven't got into functions too much, but when we do, you'll see that a bit more. So these are all things that you should remember. If you can't skim through your own code and be able to understand what's going on, or actually read what's happening, you've done a shit job and you need to do it again. If you have a variable called hello and it represents the state of your system, then you fucked up and you need to go back and redo it. So let's talk about constants. Now you notice this pi here. If I want to be a little bit of a shitty programmer, I can go pi is now equal to 4. Well, let's make it a bit true. 4.035f. And then I'm going to print out pi on the screen now. You can see that's now 4035. And then down here I'm going to go, okay, I need to print out pi times So what is it? Pi r squared. So pi times 2 times 2. And that's the diameter, circumference of my circle. 16.14 for a 2 radius circle. That's incorrect. What the fuck's happened? Now you could imagine, you can't actually see where this is defined, pi. It's in another file somewhere and you're just using it. And then some other arsehole's gone and changed it on you. How do we avoid that? Well, pi is currently a variable, so we can make it constant. Now, in case you didn't guess, a constant is a piece of data that it can never change. After you initially create it and assign the value to it, it cannot change. Excuse me. So how do we make this a constant? Well, much like everything else in programming, it's shortened. A constant is a const, C-O-N-S-T. And all you do is you just put it at the start. You can make anything you want a constant, any data type. And you'll notice the squiggly lines just come up. It's like, ooh, what's that? Expression must be a modifiable L value. L stands for left, R stands for right. So if you see L value or R value, it's generally whatever side of the equal sign it's on. Because pi is not modifiable anymore. So if I tried to build this and run it, it's actually going to say, why don't you just not be a jerk? Or it can say you can assign to a variable that is const. So if I delete this now, I don't need this anymore, and I start up the program, you'll see it's now 12.5664. That is the correct-ish circumference of a 2-diameter circle, a 2-radius circle. You can have const ints, const string, const float, const double, const whatever you want, as long as it's a data type. You can also have other const things, which I'm not going to go into because it's too much for you at the moment, because I haven't taught you about those things. And that's really it. That is everything you need to know to use, create, assign, and retrieve data. There is obviously many more advanced things you can do with it, but this is the building block for literally everything you do with data in programming in C++. There is a few little bits and pieces that you can do, and they will come in a little bit later on, and they will hopefully make sense by that point, but they're the kind of things that are rarely used. So this is basically enough for you to build any kind of just data-driven crappy program like this, to create ints, to create strings, characters, floats, constants, non-constants, etc., etc., etc. And there doesn't need to be any more talk about it. That's all your data stuff sorted. Pretty much. I say with a big smile on my face because there's so much more to go. But this hopefully is enough to get you on board with how data works in the computer. My little Excel thing is hopefully enough to tell you how memory management kind of works at an extremely basic level. And of course, I have my beautiful formula here on how to do base 10, base 2, and then if you want to do hex as well, base hex, hex base, 16 base, numbering systems, and ASCII as well. But if you have any further questions, please leave a comment below. I will try to get it around to answering them. If I don't answer them in a video, if it's just one person asking that, I will answer you directly. If I get a few questions about it, I will make sure to address it in the next video that comes out, whenever that is. I hope this has been informative because I've enjoyed talking about it, and I hope to see you next time. Goodbye.